So it is my pleasure to introduce Marco Gualtieri today in the Western Hemisphere Colloquium on Geometry and Physics. His title is Branes and Symplectic Groupoids.
Hi, and thanks to all the organizers for making this this great online seminar. I hope it continues over the next year. Okay, so I'm going to speak about a project that has been in progress for a very long time in bits and pieces. And we were stuck at various different points over the years. And so we needed various ingredients in order to get unstuck. And these ingredients came from many places. Some of the ingredients came from the Weinstein School of Poisson geometry. And some of the ingredients came from this paper of Gukov and Witten about quantization using the A model. And this project is joint with Francis Bischoff, who was my student until last year. He's now at Oxford, and Joshua Lackman, who's currently a PhD student at Toronto. And this is supposed to be an artist's rendition of a groupoid. So I'll explain that later. Okay. So the first thing that I want to explain is what a coisotropic A-brane is. Okay, so let's suppose that you have a symplectic manifold, M omega. And so we know that a symplectic manifold is the main ingredient in the A model. And in the A model, we have boundary conditions. And these boundary conditions, when quantized, become branes. And the most famous boundary conditions for the A model are Lagrangian submanifolds. But they're not the only boundary conditions. There are also these. We have a coisotropic submanifold C. Okay, so the tangent of C contains its symplectic orthogonal. I've tried to draw it here. So this orange blob is C. It has a tangent space, and then it has the symplectic orthogonal of the tangent space is lying within it. This, by the way, this symplectic orthogonal is what you would quotient by if you were doing symplectic reduction to the symplectic quotient. So this symplectic orthogonal is what's called the characteristic foliation. Anyway, besides being coisotropic, this brane is supposed to support a unitary line bundle U nabla. And what are the conditions? So the curvature of this connection, just like the symplectic form, must descend to the symplectic quotient. That's the first condition. So that means that when we, in a sense, what it means is that this unitary line bundle with connection descends or is a pullback from the symplectic quotient. Now, of course, the symplectic quotient may not exist, may not be smooth, but nevertheless, the condition is that the two form must be basic. And the second condition is that once we descend the symplectic form and the two form F to the symplectic quotient, they must satisfy this compatibility condition, namely that if you invert the symplectic form and combine it with F, it gives you a complex structure. And in fact, you can restate it in an equivalent way. You could put F and omega together to get a complex two form, and this complex two form should be a holomorphic symplectic form on the symplectic quotient, implying, for example, that the symplectic quotient must be 4K real dimensional. So it's very strong. It's a very strong constraint to have such a brane. They're quite rare, but they do show up. So let me just give two examples. These are the only two that I'm going to use in this talk. One is everyone's favorite, the Lagrangian. The symplectic orthogonal is equal to the tangent. And so therefore, the quotient is the quotient to a point. And so this curvature must be 0. And then we get the familiar fact that a unitary line bundle on a Lagrangian should be a flat bundle. And that's the notion. That's the usual notion of a brane on a Lagrangian. It's a flat bundle, flat locals, or a local system. Okay, the other extreme example is when we have a space-filling brane. So that means that the coisotropic is just the whole space, the whole symplectic manifold. In this case, the symplectic orthogonal is just 0. And so that means that the reduction is just itself. The reduction is just the identity map. And therefore, the condition is that if I invert the symplectic form, and combine it with the curvature, this must be a complex structure. So in particular, this curvature has to be non-degenerate, and the combination must be holomorphic symplectic. So this means that the only way that you could have a space-filling brane is if your symplectic manifold was secretly holomorphic symplectic. That's the only possible way you could get a space-filling brane. Okay, so let's just go back. So these branes were basically discovered in 2001 by Kapustin and Orlov, who basically looked at the simplest instance of mirror symmetry, simplest non-trivial instance of mirror symmetry, where we had a symplectic 4 torus. So the symplectic 4 torus, which you could think of as just a product of these two tori, it's a specific symplectic 4 torus, is mirror to a product of elliptic curves, a specific elliptic curve, namely the one that has complex multiplication, multiplication by I. So they investigated this, this setup where we had a known mirror symmetry between T4 and E cross E. And then they noticed that because of the fact that E has complex multiplication, there's a very special brane in the derived category of coherent sheaves of E cross E. And that brane is the graph of the multiplication by I. So this is a half-dimensional brane inside E cross E. And they said, well, this should be a mirror to something in the Fukaya category of this symplectic manifold. And they computed what its Chern classes should be. And they found that it couldn't possibly be a Lagrangian. So at that time, they realized that there could be other objects in the Fukaya category, or in the category of boundary conditions. And so they defined the following one. They said, well, if x1 and y1 are conjugate variables and x2 and y2 are conjugate variables, then let's swap them a little bit and put this and create a unitary connection with this curvature, so that when we combine this curvature with the symplectic form, we actually get something that breaks up as a wedge product of two holomorphic 1 forms and is kind of transparently a holomorphic symplectic form on T4. So they realized that whatever this object is dual to, it should have this curvature, and so they discovered the first space-filling coisotropic brane. Okay, so the problem, as it was then and is still today, is that the Fukaya category, as it's usually defined, consists of Lagrangians only. And I'll get to the issue of completion now. So, so because it only had Lagrangians, it wasn't large enough to incorporate these objects that were found by Kapustin and Orlov. And the solution that was found by symplectic geometers was to complete the category. So this completion was in 2 steps. They took twisted complexes, and they took the Karoubi envelope. And I'll get to that later. But the idea is that this is the current way of understanding where these objects should lie. But I kind of, part of this project is to have a better geometric understanding of these branes and why they might define objects in this completion. Anyway, one way of analyzing this, which I've been doing with my student Josh Lackman, is to start with some evidence coming from the fact that this T4 is really T2 cross T2, and any object in it can be used to define a transform from the Fukaya category of T2 to itself. So in this case, what you would do is, for example, take a Lagrangian brane in T2. Okay, so this is a Lagrangian with a flat line bundle, a Lagrangian circle basically in T2, and then pull it up to the T4 and tensor it with the space-filling brane. That would give you some unitary connection on a copy of T3 sitting inside the T4. And then you could try to push it forward along the projection to the second T2. And then what you find is that you can't really push it forward because the curvature is obstructing you from finding flat sections. On the other hand, inside the target T2, there's a collection of points which indicate that the fibers above those points actually have zero curvature. And not only do they have zero curvature, but the monodromy is trivial. So they're essentially Bohr-Sommerfeld fibers. And so the idea is that when you try to push this thing forward from this T3 to a T2, you can only do so over a collection of fibers. And that collection of fibers describes a Lagrangian in the target T2, and that Lagrangian inherits a local system. And so in this way, we get a transform from the Fukaya to the Fukaya. And with Josh, we just kind of really kind of went into detail to look at what this transform is, and found that indeed it really does extend to an endofunctor of the Fukaya of T2. And this endofunctor is not in the image of this map from the Fukaya of the product to the endomorphisms of the Fukaya of each factor. So this was carefully studied by Abu Zaid and Smith about 10 years ago or so. And they showed that this was fully faithful, but it was not surjective in any sense. So this endomorphism that we get in this geometric fashion is not in the image. So that means that this Fukaya category of the T4 has to be enlarged. And the usual way of doing that is to take twisted complexes. Twisted complexes is a kind of formal process whereby Lagrangian objects, you take formal sums of them, you take shifts of them, and you take cones of morphisms between them. And if you allow all of this, you get the twisted complexes. But in fact, that extension is not sufficient. You also need to do this idempotent completion. Idempotent completion is necessary in order to get this, this particular object that we studied. So it's still unknown and probably not true that coisotropic A-branes are always in this completion. That's a still unsolved problem. Whether we can understand space-filling branes or other coisotropic A-branes just by doing this completion, that's unknown. Okay, so let's move away from I just wanted to introduce the topic of coisotropic A-branes, and now I'm going to use them to study Kaler manifolds. So if there are any questions about A-branes, I'll take them now.
We had some questions in the chat, but they've been answered.
Okay, great. I hope some of my students are in the chat doing some work, but thank you to the people answering questions. That's great. It's something we don't usually get in conferences. Okay, so how can we use this for Kaler geometry? Well, there's a very interesting thing you can do with space-filling branes anytime you have a Kaler structure. So let's look at a particular symplectic manifold, the cotangent of the manifold N. It's equipped with the canonical symplectic form, which, as we know, is exact. So inside this symplectic manifold, we have everyone's favorite Lagrangian, which is the zero section, equipped with the zero local system, with the trivial local system. But we also have a space-filling brane whenever N is equipped with a complex structure. As soon as you give me a complex structure on N, which is compatible with, as soon as you give me a complex structure on N, okay, we get a space-filling brane on the cotangent bundle of N. And that space-filling brane is just the whole of the cotangent bundle, but it's equipped with a unitary line bundle, which is the trivial bundle, but with a non-trivial connection, d plus I times I star theta canonical. So this is the complex structure applied to the canonical one form, used as a connection one form. The curvature will be I star applied to the canonical symplectic form of the cotangent bundle. And so when we put the curvature together with the symplectic form, what we get is the holomorphic symplectic structure on the complex cotangent bundle. Right? We all know that if you have a complex manifold and take its holomorphic cotangent bundle, that will be holomorphic symplectic. And indeed, that holomorphic symplectic structure is coming from a space-filling brane on the underlying real symplectic manifold. Okay, so in this sense, the complex structure is encoded in the space-filling brane on the cotangent bundle. Okay, and then now in addition to the complex structure, I'm going to also request a Kaler structure. So now N is going to be equipped with a complex structure and a Kaler metric. And in this case, actually, let me assume that it's pre-quantized to a unitary connection on N, whose curvature is the symplectic form. Okay, and then what I can do is take this pre-quantization and pull it back to the cotangent bundle and tensor it by the previously defined trivial bundle and add the connections together. So now this will be the connection whose curvature is the real part of the holomorphic symplectic form. And this one is the one whose curvature is the symplectic form. And the resulting holomorphic symplectic structure that we get is different from just the holomorphic cotangent bundle. So the complex structure is changed. So this is the original complex structure on the holomorphic cotangent bundle, and it's been modified by the combination of the Kaler form and the canonical symplectic form. These two combine to give a deformation of complex structure. This is a non-trivial deformation of complex structure. And then the holomorphic symplectic form is also affected by adding this topologically non-trivial 2 form. So this is sometimes called a magnetic deformation, and this is sometimes called the twisted cotangent bundle. So this is a deformation of the holomorphic cotangent bundle into the twisted holomorphic cotangent bundle. Okay, and so this is how I want to interpret a Kaler structure. The Kaler structure is giving me a deformation of the holomorphic cotangent bundle of a complex manifold into this twisted cotangent bundle. Okay, and by the way, the twisted cotangent bundle is not a vector bundle. It's an affine bundle, because you can see here that because the complex structure has been modified, the 0 section is no longer a complex submanifold, and in fact, it doesn't have any complex sections. It's just an affine vector bundle. I mean, it's an affine bundle for the holomorphic cotangent bundle, but it's not isomorphic as a complex manifold or as a vector bundle. Okay, so the fact that we get this interesting interpretation of a Kaler structure, it's very reminiscent of something that was introduced by Gukov and Witten about 14 years ago or so. So they introduced a kind of a new approach to geometric quantization. So their idea was that if you have a symplectic manifold, what you should do is you should realize it. So the idea is realize your symplectic manifold as I'll call it as a submanifold of a complexification, a manifold of twice the size, twice the dimension, in such a way that the complex symplectic form, when I restrict it to this submanifold, we recover the symplectic form that we started with. So their idea was a little bit odd. It was the idea that if you wanted to quantize a symplectic manifold, what you should do is express it as a submanifold of a twice larger manifold, which has a holomorphic symplectic structure. And notice that this is real, and this is a holomorphic symplectic. So what this implies is that the imaginary part of the holomorphic symplectic structure should restrict to the submanifold to be 0. So this was the kind of bizarre idea that your symplectic manifold, your real symplectic manifold, should be expressed as a Lagrangian inside a holomorphic symplectic manifold. And in this way, what you would get, their idea basically hinges on the fact that the original manifold would be represented as a Lagrangian brane inside this complexification. Okay, but in the complexification, because it is a holomorphic symplectic, then that complexification would have a space-filling brane relative to the imaginary part. So you basically have a situation where you take the complexification, you look at its imaginary part, that's a real symplectic manifold, and it has an A model. Okay, and that A model has two branes in it, and the pair somehow encodes the original symplectic manifold. Oops. Okay, and so once you are in this situation where you have an A model and you have two branes, then you could produce two algebras and a bimodule between them. You could take the endomorphisms of this brane, you could take open strings from L to L, you could take open strings from Z to Z, or you could take HOMs between them. So now you use the categorical structure on the A-branes to produce a vector space and two algebras acting on the vector space. And they carefully went through a bunch of examples, including the simplest example, which is just the cotangent bundle of the two-sphere. So the cotangent bundle of the two-sphere is the complexification of the two-sphere. We think of it as being deformed in the way that I described before to a twisted cotangent bundle. Okay, and this twisted cotangent bundle had these two branes in it, a space filling and a Lagrangian. And the idea was that taking homomorphisms from the Lagrangian to the space filling brane gives you the geometric quantization. So it gives you the space of holomorphic sections of the O1 line bundle. Whereas taking strings from Z1 to Z1 would give you an algebra, and they identified this as a quotient of the universal enveloping algebra of SL2C with, with total angular momentum being fixed. Okay, so this was their approach to quantizing the Kaler structure on P1, expressing it as a Hom space in the A model. Okay, so just so what I'm trying to point out is that Kaler structures fit into the Gukov-Witten framework. Okay, this may not have been obvious at the time. So anytime you have a Kaler structure, you have a twisted cotangent bundle, and inside that space we have two branes, the Lagrangian zero section and the space-filling brane. And you can do exactly as Gukov and Witten did, and in fact, one of the examples they worked out is a particular case of this Kaler example. So just summarizing the idea, the Kaler structure on N is encoded by a pair of branes inside the cotangent bundle of N. One of them being Lagrangian and the other being coisotropic. And the geometric quantization of the Kaler structure on N is encoded by the Hom space between these two branes. Okay. Okay, now, before I stop for questions about this basic idea, I just want to point out what the major problem with this idea is. And this is the same problem that they had in their paper and that we have in our work, which is that the definition of homomorphisms in the A model between Lagrangian and space-filling branes is not well defined. All of the work in the Fukaya literature focuses only on Lagrangians, and it doesn't really explain how to compute Homs from Lagrangians to space-filling branes. So there's basically only a few papers where this has been done rigorously, and they're in the physics literature, and they're, let's say, very difficult to generalize. So there's a paper by Aldi and Zaslow where they did it exactly, but they depended on being able to exactly solve the system, the A model, I mean. And then there's some papers by Witten and Kapustin and Witten, Gukov and Witten and Gukov, where they do some special cases and they kind of appeal to some localization arguments which are not always available. In any case, the main problem is to define this. So in our work, we needed to propose a definition that would at least work for our examples that we were interested in. And that proposal is listed here. So common to all the approaches, like all of the papers who have computed this Hom space, in every case, you could argue that the authors introduced a holomorphic Lagrangian polarization of the space-filling brane. Okay, I know that this is not thought to be necessary, not considered to be necessary, but in any example where I've seen a computation, it has been chosen. So I don't know what to do. I have to do it. So I'm going to do it. A holomorphic Lagrangian polarization. And we have worked on some examples where the polarization is not smooth. It's not a smooth foliation. It can have singular members, but I don't know what the full definition should be. All I have is a large family of examples. The next step is to lift the prequantization of the symplectic form to a holomorphic prequantization of the space-filling brane. So what we need is the holomorphic symplectic structure, which is present, to actually be the curvature of a holomorphic connection. And this is very strong. For example, if you were working on a compact hyperkähler manifold with a holomorphic symplectic structure, you would never be able to pre-quantize it in the traditional sense. You would never be able to find a holomorphic line bundle with holomorphic connection whose curvature is that holomorphic symplectic form. Nevertheless, in all of the examples that seem to work, this is possible. The next step is to take holomorphic flat sections of this holomorphic prequantization along the polarization leaves. And this brings in this Bohr-Sommerfeld condition, except that it does so in the holomorphic category. So what that means is that it makes sense to do a push forward of the holomorphic flat sections along the leaves. And what you'd get is a coherent sheaf on whatever the parameter space is for your polarization. So this is a kind of holomorphic version of what you normally see in geometric quantization. And then you should take global holomorphic sections on the parameter space of whatever this polarization is. Okay, and so a kind of the simplest example of this working would be to take this twisted cotangent bundle and to use the fibers, the affine fibers, as your holomorphic polarization. It's a Lagrangian polarization. And then you could take flat sections of the holomorphic prequantization along these fibers. And when you do that push forward, what you do is you basically recover the complex structure on the line bundle that would be defined in the usual way by taking the 0-1 part of the Chern connection. And then by taking Homs, and the parameter space in this case is just the projective, whatever the complex manifold is that you started with, and you would get, N. And you would get the holomorphic sections of the line bundle in the usual, which is what you would expect. Okay. Okay. Right. Okay. So this is the basic idea that the Kaler structure determines these two branes. We want to take the Homs between the two branes, and we have some proposal for how to do it. Okay. And the last kind of part of the idea is that these branes, we should be able to create more and more of them. We should be able to create a sequence of them. And all of the geometric quantizations that we get from that sequence, all of those vector spaces should assemble to produce a graded algebra. Now, why do I say that? Well, we know that in Kaler quantization, if you take the geometric quantization of omega, let's say your Kaler form, you can also then take powers of omega, or you can multiply omega by integers. And you can take a sequence of geometric quantization, getting larger and larger. And then when you put these all together, you get the usual algebro-geometric coordinate ring for your complex manifold. So it's kind of the essential step of going from geometry to algebra is to assemble all of the different geometric quantizations of the powers of the symplectic form all together to make an algebra. And what I want to observe, and this is the key observation for the rest of the talk, is that the reason why this is possible to do is because the cotangent bundle has a very simple structure, the structure of addition on the fibers. So let me explain what I mean. So there's an addition map given two covectors. You can just add them together. And this addition basically defines a correspondence from the cotangent cross itself to the cotangent. And this relation is a Lagrangian relation. So what that means is that you can take branes in the product of two copies of T star m, and you can transport those branes to T star m. And if you do that with the space-filling brane of a Kaler form, and if you transport it over, what you will get is exactly the sum. What you'll get is exactly the sum of the Kaler form with itself, and you'll get a second space-filling brane, where basically you just double the symplectic area of everything, right? And so what this means is that you're going to get a sequence of branes, space-filling branes, one for each integer. And then you could also say that there's a sequence of Lagrangians, but the problem is that the Lagrangian is idempotent. If you try to convolve the Lagrangian with itself, you just get the Lagrangian back again. So you basically have a pair of branes, and you have a sequence of pairs, right? And you can take Homs between them. So this is the ith geometric quantization, and this is the jth geometric quantization. And because of the way that the symplectic manifolds are related, there's a tensor product map from the I tensor J space to the I plus J space. And you can interpret this as being the origin for the algebra structure that we know and love on any Kaler manifold, a pre-quantized Kaler manifold or polarized Kaler manifold. Okay, so I just wanted to kind of make a connection, and that was the second part of my talk. I wanted to connect the Gukov-Witten approach to geometric quantization with, let's say, the quantization of Kaler manifolds and also the determination of the algebra associated to a Kaler manifold. And I'll take questions on that if there's any.
Well, there's a question from back earlier from Yuan Yao. Does this A-branes story fit into the story that Lagrangian correspondences induce functors of Fukaya categories /
Yes.
two category story?
Yes, exactly. So that's what's happening here, is that you have a Lagrangian correspondence from the Lagrangian correspondence from this cotangent bundle cross itself to itself. This means that the Fukaya category of T star m should be monoidal in some sense. At least it should be monoidal on some subcategory or something of that nature. And that's been studied in the literature on Fukaya categories. I know that Denis Auroux has had some students who have looked into this. Alexander Subotic, for example, I think looked into this. So there, and also James Paskalev, who I've spoken to a great deal about this. He's probably in the audience. So anyway, the point is that there is a structure of the cotangent bundle which renders the Fukaya category monoidal, and that monoidal structure is being used here in order to extract an algebra. Okay, now, was that the only question?
Yes, that was the only question.
Okay, so this idea that you can take points of the symplectic manifold T star m, and you can combine them together, which is just the normal fiber-wise addition. Okay, this composition operation is a special case of something called a symplectic groupoid. Rather than a symplectic group, the reason it's groupoid is because in order to be able to add the 2 points in the cotangent bundle, they have to satisfy a constraint. Namely, they need to be in the same fiber. It's only if they are in the same fiber that you can add them together, and it's for that reason that it's called a groupoid. So what is a groupoid? Well, this cotangent bundle with its canonical symplectic form, this is the quintessential example of a symplectic groupoid. A symplectic groupoid is just a Lie groupoid. It's a space of arrows. It's a manifold of arrows which go from and to some points on another manifold. So this is the base manifold N of objects, and this is another manifold consisting of arrows which have a source and have a target. The source and target are points in the manifold N, and these are arrows that join those points together. And if the source of one arrow coincides with the target of another arrow, then you can compose them. And that's this combination operation. the composition in the category. So I've drawn the composition here, M. It is a map, a smooth map from the fiber product of the space of arrows with itself to the space of arrows. And the condition of being a symplectic groupoid is that if you if you pull back the symplectic form on these two fibers, it should agree with the pullback via the composition map. And I've written it over here. So this is the compatibility condition. So these are very, these were introduced by Alan Weinstein and have been studied for decades in the symplectic school, in the Poisson school. They're very useful for studying Poisson manifolds. The reason for that is that this space of arrows, it has, oh yeah, so I usually draw groupoids this way. So it's a space, the points in it are arrows and they go from this point to this point. So you should think of this point as being an arrow from S of G to T of G. Anyway, the point is that if you take this symplectic structure on the groupoid and you push it forward by the target map or the source map, it is possible to push not the symplectic form, but its inverse. You could push that Poisson structure forward, and what you'll get is a Poisson structure on the base manifold. And so these are very attractive because they basically they act like desingularizations of the Poisson structures. You can, if you don't like studying Poisson manifold, what you could do is you could try to construct this groupoid over it, which is symplectic and which recovers this Poisson structure just by push forward. So the cotangent bundle is a very simple case where it's a bundle of abelian groups. The source and target maps agree, and they agree with the bundle projection. And if you push forward the Poisson structure on T star n down to the base, there's no surprise, you'll get 0. So you'll get the 0 Poisson structure. So this is a symplectic groupoid for the least interesting Poisson structure. Okay, so now I'm going to explain a very explicit way that you could modify the cotangent bundle to make it much more interesting. So how could you do that? So I'll try to go through this in detail. So suppose that you had a toric Kaler manifold. So this is the case that we're most interested in for the moment. So N is a toric Kaler manifold, and we're going to consider its cotangent bundle. So we know that there is a C star to the N action on N. The action is rho. And what I'll do is choose what's called an R matrix. An R matrix is a bivector in the Lie algebra of this action. So it's in wedge 2 of the Lie algebra. And the idea is that the elements of the Lie algebra in this case, they commute with each other. So this R matrix satisfies what's called the classical Yang-Baxter equation because its Schouten bracket with itself is 0. That's just because this is an abelian Lie algebra. Okay, so what does that mean? That means that if I push it forward under the action, what you'll get is a bivector field on N, a holomorphic bivector field on N. And that holomorphic vector field must satisfy, must be a Poisson bivector, because if we take the Lie bracket with itself, it'll be 0, because this action map is a bracket preserving map. So this is a very easy way of producing a holomorphic Poisson structure on a manifold, on a complex manifold. You just push forward an R matrix. Okay, so now we have now we have a holomorphic Poisson structure on N, and this thing is invariant under the action of the complex torus, basically because it's made it's actually made of generators for that torus action. So of course it will commute with the torus action. Now the interesting thing is that although the complex group does not act in a Hamiltonian way on the Kaler manifold, because of course it doesn't preserve the Kaler form, the complex group. This does act on the cotangent bundle, the cotangent bundle of n, and this action is Hamiltonian. So what I'm going to consider is for now I'll consider the holomorphic cotangent bundle. So I'll think of the cotangent bundle of n as being equipped with this holomorphic symplectic structure, and this complex torus action is complex Hamiltonian, and so it has a complex moment map to the complexification of the Lie algebra. So we have this moment map for the torus action on its cotangent bundle. Okay, and then I'm going to use this to deform the structure of the cotangent bundle. So what I'll do is change the source map. So I'll say that if you had a point in the cotangent bundle, which originally was thought of as an arrow, right? I mean, originally, if you take the cotangent bundle and we took a point in the cotangent bundle, then we could think of that as an arrow which goes from the base point to itself. In other words, the entire cotangent fiber is just an isotropy group, which goes from the point to itself. But now I'm going to deform the projection map. This is the projection map, which takes the covector to the base point. But I'll deform it by the following. So I'll take this element of the cotangent bundle and apply the moment map. That will give me something in the dual of the Lie algebra. And then the R matrix, I can contract that element of the dual of the Lie algebra. I can contract it onto the R matrix, and that will give me something in the Lie algebra. And then I can exponentiate that to a torus element, and that torus element will act on this point of the base. Okay, so in this way, and there's a minus sign here. So in a way, I'm using the torus action to take my covector, project it down, and then drag it by the action of the torus. And the amount that I'm going to drag it depends on the value of the moment map, of this complex moment map. And then the new target map will be similar, except that I'll use a plus sign. So I'm going to drag it in the opposite direction. So now the original projection from the cotangent to the base has been split into two different fibrations. And as a result, now it becomes more tricky to determine when two covectors can be composed, right? Because now they are actually arrows which have a non-trivial action on the base. And so we need to make sure that the two covectors are in different fibers, but that they agree tip to tail so that we can compose them. And that composition is written here. And notice here what's happening is that I have the same group elements as before, but these group elements are not acting on the base. They're actually acting on the cotangent bundle itself. So now I need to use the cotangent lift of the action of the torus and actually move these covectors around in the cotangent bundle and then add them together. So what this multiplication is basically doing is it's taking the 2 points in different fibers and it's dragging them into the same fiber and then adding them together. That's basically what this is why it makes sense to make this addition here. Okay, and so in this way we deform the structure of the cotangent bundle. And I just want to make an aside here. So if we take the cotangent bundle, okay, and we do this change, so now instead of having only the fibers of the cotangent bundle, I have two foliations like this. These are the fibers of the new source and the new target map. And I just want to point out, this is not the focus of my talk, but people have heard me talk about generalized Kaler structures at length in the past. And I just want to point out that by deforming the cotangent bundle in this way, one side effect of that is that the zero section is going to now inherit two different complex structures because it has two foliations, two holomorphic foliations that are transverse to it. So if I take the complex structure of this ambient space and if I push it push it down along the red foliation, I will induce on the original manifold a certain complex structure, which I could call I plus. And if I do the same thing with the green foliation, with the target fibers, I'll get I minus. And these are now two different complex structures which form a generalized Kaler structure. So I just wanted to point out that this type of groupoid deformation is basically equivalent to a generalized Kaler deformation. That was the content of this paper from 2018 with Zabzin and Bischoff about generalized Kaler structures and groupoids. So anyway, the point is that we are now, by doing this, by making this deformation, we're moving from Kaler to generalized Kaler. Okay, so the first part of my talk was kind of explaining how Kaler fit into the Gukov-Witten framework. Now I'm explaining that generalized Kaler fits into their framework as well. Okay, so anyway, now we have a groupoid. And I should say that this method was developed by Weinstein and Ping Xu, in 91 and 92. So this was part of their original study of, this was at the time where they were just trying to find examples of these symplectic groupoids. And this was one of the earliest family of examples that they found. Okay, and then this space-filling brane that I had on the cotangent bundle, turns out that it also has to change. So it doesn't have to change in a very dramatic way. The way that it has to change is that so the same structure can be used, but the problem is that now because the multiplicative structure of the groupoid has changed, it turns out that if I want this brane to be multiplicative, if I want it to respect the multiplication, I need to modify it on the composable arrows by using a groupoid 1 cocycle. And again, this piece of data, which is just it's just a C star factor, it comes directly from the R matrix. Oops, that should be R. Actually, these tensors C should all be R. So the R matrix is the key ingredient that allows you to convert the moment map into an actual action. And the moment and this R matrix gives us a C star element associated to every pair of composable arrows. So the basic idea is that if you have a fiber of this line bundle, of this space-filling brane over one arrow, and you have the fiber over another arrow, what I want them to do is to compose by tensor product to give the fiber over the composition of the arrows. And that works well, except for the fact that the connection doesn't quite agree. And so there's a scale factor in order to identify the connections on both, on that tensor product compared to the result. And that factor, which measures the difference of connections, is exactly this cocycle. So this is an important part of the deformation. And this exactly the same procedure of deforming in this way, it works to deform all of the branes that I had when I took the different powers of the Kaler form. So now for every multiple of the Kaler form, I get a space-filling brane inside this symplectic groupoid where the structure has been kind of modified from the cotangent bundle. So this is all the data now that I had before. All of this. All of this. So I have the cotangent bundle, and I have a sequence of space-filling branes. Remember that this is how I built the algebra. So now I have kind of replicated all of the elements of the setup But in a case where the groupoid is not abelian, the groupoid is much more complicated. Okay, so so there is nothing stopping us now from computing the Z-graded algebra. So we need a holomorphic Lagrangian polarization. So as is always the case in geometric quantization, the difficulty is in finding the polarization. But in this case, we have a toric manifold, and we have this holomorphic moment map J from before, and this thing, this map turns out to be a groupoid homomorphism from the cotangent bundle to an abelian group. And this fact, the fact that this is a holomorphic groupoid morphism, it's in the face. And so what do we need to do? Well, according to the proposal for how to compute HOMs, right, I need to take holomorphic flat sections along the Bohr-Sommerfeld leaves, which intersect L, because I'm trying to take HOMs from the space-filling brane to the Lagrangian. So basically the idea is that the Bohr-Sommerfeld condition, it kind of dissolves the space-filling brane into a bunch of Lagrangians. And then once I have those Lagrangians, then I can just take regular HOM from those Lagrangians to the Lagrangian L. Oops. All right, so if I implement that, so Francis Bischoff and I have been implementing this in this example and others. And what you get is that for the 0th space-filling brane, we get a single Bohr-Sommerfeld leaf, which intersects L, the 0 section of the cotangent bundle. And for the first space-filling brane, we get these 3 integer points. I'm talking about, oh, I'm sorry, I should have said this is for CP2 with the standard Fubini-Studi Kaler form. I'm just giving you an example where for each space-filling brane, the Bohr-Sommerfeld fibers are in correspondence with the lattice points in the corresponding Del-Zant polytope. So this works in exactly the same way for any toric variety. And then when you take the holomorphic flat sections along the tori fibers for this holomorphic connection, there's a canonical identification with the usual holomorphic sections of the OK line bundles, or of whatever your ample line bundle is. Okay, so far everything is as it would be in usual toric geometry. But then the problem is that when you multiply these branes with each other, you have to use the convolution product of the groupoid structure, and that's where you get these dragging. These different sections are going to be dragged to and fro by the source and target maps. And so as a result of that, what happens is that when you take, these are, for example, 2 toric monomials, which could represent, let's say, generators for 2 of these dots. And if we take their convolution, the procedure is telling us to drag one of them by this torus action on the cotangent bundle, drag the other, take their tensor product, and then apply the groupoid cocycle in order to be mapped into the third space-filling brane. And if you work this out carefully, then you see that what you get is the usual tensor product modified by a certain group cocycle, which depends on the weights on which monomial I had chosen. So depending on which monomial you pick, you'll get different weights. So the result of this, is that you get a non-commutative algebraic toric variety. This is a kind of quantization of the complex structure of the toric variety. Right, and at the moment, what we're working on is extending this to CP2 where with a holomorphic Poisson structure, which is non-toric, all of the obstructions for making this procedure work vanish in this case for all of the holomorphic Poisson structures on CP2. So we're expecting to be able to do this. The only challenge is in finding the polarization, this holomorphic Lagrangian polarization. And it turns out that finding this Lagrangian polarization is very much closely related to the work that Oru and his students have been doing on finding special Lagrangian polarizations or special Lagrangian foliations of symplectic manifolds of Del Pezzo surfaces in the complement of the anti-canonical divisor. That is very relevant to this problem. And it actually does provide this holomorphic Lagrangian polarization in some cases. Okay, and so the idea is, so the hope is that in all of these cases where we have a very nice algebraic deformation of a homogeneous coordinate ring, for example, the Skleanin algebras or all of the various non-commutative algebras that are studied in Artin's school, Artin Tate Vandenberg school of non-commutative algebraic geometry. The idea is that they might be expressible in terms of this type of holomorphic groupoid geometric quantization. And maybe just to indicate one thing for the future is that this there is nothing stopping us from implementing the same idea for other generalized complex structures besides holomorphic Poisson structures. So we could take a general generalized complex structure, and we know that any GC structure has an underlying real Poisson structure, and that if that Poisson structure is integrable to a symplectic groupoid, then we would have a symplectic candidate for an A model approach to studying GC manifolds. So this is kind of indicating that when you have a generalized complex structure, there is an A model potentially in the background, which could be used to define a Hom space between any two generalized complex branes. This is something that we've been looking for a long time. And the idea of kind of reducing the problem to an A model computation is very attractive. Unfortunately, this would require that we understand how to compute morphisms from a Lagrangian to a coisotropic A-brane, which is more general. So I definitely encourage everyone who's interested in these coisotropic A-branes to work out examples and start making these computations. Okay, thanks for your attention.
Thank you, Michael. Great talk. So all questions in the chat have been answered.
That's excellent.
At this point, let me just invite participants to ask questions by raising their hand in the chat, in the participants menu, I mean. I guess, Greg, you have a question? Could you unmute yourself, please?
Yeah. Okay, this might be a stupid question, but has there been any study of Hom from a Lagrangian to a coisotropic brane in the Landau-Ginzburg context in the Fukaya-Seidel category?
No, no, I don't. Not that I know of. No. The list I gave is really. I hope it's an exhaustive list. If anyone knows any other papers besides the ones I listed, let me know, because yeah, they're few and far between, and they're always between. They're either between a space-filling brane in itself or a space-filling brane in a Lagrangian. But yeah, that's a good question. Even in the gauge linear sigma model, if I guess that's what you. Well.
No, I had in mind just a general Fukaya-Seidel category.
Right.
I call it in a holomorphic Morse function.
Right. But even in gauged linear sigma models, it should be, yeah, there should be some more work done for these coisotropic ones.
Okay. We have another question from Sharyar Sikandar.
Hi, thank you. I was just wondering if the Gukovitin picture works in families as well. So you fix a symplectic manifold N, but there's a family of Kaler structures on it.
Right. Well, so the idea, the idea that I'm using here is essentially to represent geometric data in terms of branes, collections of branes, right?
Mm-hmm.
And these are topological branes in the these are branes in the A model, okay? And we know that, the fundamental idea of mirror symmetry, right, is that the moduli space of branes is a complex manifold. The moduli space of A-branes is a complex manifold. And so it certainly makes sense to consider holomorphic families of A-branes. Because if you look at how the theory is defined, right, if you have a holomorphic family of boundary conditions, then the results of the theory all depend holomorphically on that parameter.
Mm-hmm.
So the answer is yes, but no one has studied that. Somehow doing things in holomorphic families is very important for what I'm saying, because I'm doing these deformations, and these deformations are holomorphic families of algebras.
Right. Okay. It's I mean, just to put it in the standard context of geometric quantization, if you have a manifold, if you have a parameter space for all the Kaler structures, you should get a not really a vector bundle, but a bundle whose fibers are these homes from LT to AT. AT is the parameter there, but I mean these Lagrangians L and A, which will depend on the parameter space.
Yes. Yes.
And this bundle or whatever this thing is should have a flat connection as well.
Yes, I'm very well aware of that. Yeah.
All of this works out, or?
I'm sorry?
All of this actually works out in the.
Well, I mean, like I said, this recaptures the standard geometric quantization. So it's
okay. That makes sense.
It's not. Yeah, it's not a mystery why that would work out. Yeah.
I see. And I had a small question about the Kapustin-Orlov mirror example.
Yes.
Well, so if you can just say a word, why in the mirror do you get a copy of this elliptic curve which has multiplication by Gaussian integers? And if it is possible to obtain other mirrors which are also products of two elliptic curves, but which have CM by orders in some other complex.
The complex multiplication is not that significant. It's just the example that they looked at because they knew that there would be a special brane that is not normally present in the case of E cross E, where E has complex multiplication. But in fact, you could take different elliptic curves, and you will find, in some cases, for example, if there's a relationship between the tau parameters of the two elliptic curves, which would allow there to be some kind of complex relationship between them. For example, if there was an isogeny or something,
well,
that isogeny will have some. That isogeny would have some brane associated to it, and that brane would appear in the Fukaya category. And then you could ask whether that is Lagrangian. And it's easy to produce examples which could not be described in a Lagrangian way.
I see. So this would work if you take tau and tau prime to be two Heegner points of the same discriminant. I mean, that would ensure that the two.
Yeah, I don't study the problem, but like I said, it's not important that it has complex multiplication.
Thank you.
Okay, our next question is from Alex Chiquita.
Hi, Marco. Thanks for.
Hi.
I'd like to ask if you, or if you know if anyone else, has studied anything relating these coisotropic branes, sort of before you take the before you take homotopy category. So, does anyone know what role they play in sort of enriched structures and infinity or what have you?
You mean before taking without taking these completions that I discussed?
Right. Yeah. Because I imagine you're working.
Well, I mean, the point is that no. I mean, the point is that they. I mean, pretend that you didn't know that you should take certain completions, right? Then these objects would tell you that you should. They for example, these. I mean, that was the point.
You're
was the
working on it
point
after
of-
taking homotopy category, right?
That was the point of this computation. You have an object inside T4, which is supposedly an A-brane,
Mhm.
and you can use it to define a geometric functor, a functor that has a geometric definition.
Mhm.
That functor relates the Fukaya category of T2 with the Fukaya category of T2. Right? So there's no completion being done here. It's just a genuine geometric object inside T4, and it's giving you a functor for Lagrangian objects. And the question is, what is this functor? And the answer is that it is given by that this operation is in this completion.
Right, right. But the functor you constructed is between the sort of derived to K categories. Is that correct?
No, not necessarily. No, you just take Lagrangian objects. You could just take regular Lagrangian objects and transform them over.
Okay.
It would just be like a Fourier-Mukai transform. You can do a Fourier-Mukai transform. You get a coherent sheaf.
Mhm.
You know, you don't necessarily need to work in the derived category.
I see.
So they do have a realization in some way before taking this completion.
I see. Thank you.
We have a question from Maxim Kontsevich.
Actually, it's not a question, more like comment. Yeah, you ask the first part of your lecture whether, in general, this adding extensions and direct sums to Fukaya category can get coisotropic branes. No, definitely the answer is no. You just can cook up high-dimensional torus with constant symplectic form, which has no Lagrangian submanifolds whatsoever. So Fukaya category will be 0, but there are plenty of coisotropic branes. Yeah, I don't know, Marco, have you seen, I gave a lecture about a year and a half ago in Miami. That was on some video you can find on Diniaru homepage.
Okay.
Discussing in detail this how this coisotropic branes should look in high-dimensional tori and so on. Yes.
Ah, interesting. Okay,
Okay,
great.
okay.
I'll take a look.
I will send you the link. Yeah, okay.
Thank you. Thank you. Well, that's good to hear. So they are more mysterious than many people think.
Are there any further questions?
Sheldon, there are questions in chat.
Okay, I didn't see that came in. Oh, thank you. A new one came in. Yes. So let me. So I see you have it. Yeah. So I guess the first question. There are two questions in the chat. Then, Lisa, Jeffrey, Lisa, do you want to unmute yourself and ask the question?
Yeah.
Or,
Thanks for a wonderful talk, Marco. I just wondered, when you defined the convolution, why did you need to put the factor of pi multiplying the C? Couldn't you have incorporated this factor into the definition of C?
Yes, that's true. Yes.
I mean, was there some reason why C is supposed to be, it's supposed to be special, but C takes integer values or something?
No, but in practice, we were taking certain integer R matrices, so that was the reason for it originally. But yeah, there's no reason.
Okay, thanks.
okay. And there's another chat question from John Huerta. John, would you like to ask the question yourself? All right, I could just read it. Is A the deformation of a commutative algebra? What's the deformation parameter?
No, sorry, maybe it wasn't clear that the entire point of this was to use the fact that the groupoid is non-trivial now to explain the fact that this deformation is a non-commutative graded algebra. So this is a you could think of this as a degeneration of it's a toric degeneration of the Sklianin algebra. So, you know, normally the Sklianin algebra is thought of as the non-commutative deformation of CP2 given by a smooth cubic curve. And if that degenerates to a triangle, it would become toric, and this would become a non-commutative toric variety. So that's what you get from this construction.
Are there any further questions? I don't see any in the chat or raising hands. If not, let me welcome you all back for next week's talk by Laura Fredrickson, and take this opportunity to thank Marco once again for a great talk.
Thanks again to the organizers. Great.